Hello, everyone. Welcome to this interview with Professor Jiannis Pachos. Professor Pachos works at the University of Leeds in the School of Physics and Astronomy and is a professor of theoretical physics. Professor Pachos is the author of Introduction to Topological Quantum Computation. Here's my copy, which I have fond memories of reading during my PhD. I should read it again, really. So Professor Pachos, he was advised me during the second half of my PhD at the University of Leeds, and I'm really pleased that he's joined me to discuss his thoughts on physics and his research interests, which, along with topological quantum computation, include things such as simulating quantum field theories and quantum gravity, even in the laboratory, which we'll get onto in due course. So, welcome, Jiannis. Thanks for joining me.
Thank you very much. I'm flattered for inviting me.
No, it's my pleasure. Thanks. Thanks for taking the time to be here. So, if we go back to kind of your formative years, if we start there, you grew up on the island of Rhodes in Greece. And
that's right. Yes,
I hear it's a very pretty island, and with all the sunshine, beaches, and no doubt many other distractions, how did physics manage to grab your attention in the first place?
Yes, so we also have schools and university and so on.
I'm surprised.
So yes, at the beginning I enjoyed at school solving maths problems, the simple ones and so on, and subsequently I quite enjoyed solving physics problems. It's just little exercises, sometimes not related to school really, finding from books here and there. We had a really nice library that nice. I could just pick up things. So that created my interest in this type of area. And subsequently, my cousin, who was much older than me, he went to the university studying physics, and we discussed a lot, and that settled it for me for studying eventually, going to the university, just to meet other people who enjoyed physics and could discuss with them and learn more, really.
Okay, so your cousin and him studying was an influence on you in your decision to study, right?
I think yes. We eventually we even collaborated later on when I finished university, my PhD. We even wrote papers together. So I'm really proud of achieving this child dreams. Yeah,
that's great. So was there any particular area that you found really inspiring and kind of provided extra motivation for you to study physics at University of Athens?
Yes. So even before going to the university, I was reading about relativity, Einstein's theories, which is special and general relativity, which are very unconventional in a sense. So, they exist, they're real, they should happen, but the logic they have is quite different from our everyday experience logic. So that grabbed my attention as a philosophical, if you like, a challenge, as well, intellectual as well. And that's what I studied also at the university. I jumped, we have a special relativity on the second year and general relativity on the third year. And I took actually general relativity already on the second year before the special relativity, because I was quite eager to get both of them done. That and I continued doing projects on it. So that inspired me really a lot. Later on, it was I got in touch with studied quantum physics, and that was completely blew my mind. All the historical challenges that we hear about quantum physics and how scientists in last century struggled with it, even Einstein and so on. A student goes through these things as well. So, which is a very exciting intellectual game until you find a way how to understand. It's a very strange theory, and how you accept it and how you connect it with your previous knowledge is always something that puzzles students.
I'm just curious, at what stage were you introduced to quantum physics when you on your degree?
Okay, it might have been third and fourth year. So
wow.
4-year studies. Yes, that's right.
That's really interesting that it was introduced at such an early stage, because these days in universities, at least in the UK, students already have introductory courses on quantum physics from year one, and
that's right. Yes, if not at school, yes.
Yeah, even at school. Yeah,
that's right. Yes.
You didn't even you didn't start you had no introduction to quantum physics at school even?
Not at all. Not at school and at the university. The first 2 years they were quite not it was about any other physics, classical mechanics and so on. So and relativity, and then the third and fourth year is a 4-year degree. So we did quantum physics. I remember I did buy a book before that, in order to an English book to learn quantum physics, and I won't mention what book, the author, but it was a really old-fashioned book and it gave me a really hard time. Thankfully, I had very good lecturers, and we discussed a lot at the breaks between lectures on quantum physics, and gave the usual questions and trying to explain it, and discussions emerged with other students, and really that's what matures you and makes you understand the topic better, I think, especially for quantum physics.
But it sounds like you had a really solid and rigorous sort of training in classical physics, which is actually no bad thing, right, in itself, right?
That's right. Yes, I did enjoy that at the time.
So if we skip forward to like your final year of your degree, you actually went to the University of Sussex and did a project under the late Professor David Bailyn. What was that experience like? How did it shape your early research interests?
That was fantastic. That was, again, my cousin, the physicist, was doing a PhD with Professor Bailyn, David Bailyn. And so I went there to do my final year project. I enjoyed it very much. That was in Sussex. Brighton is a great city to live. And I made many friends that lasted up to now. And the research there was quite exciting for me, getting into the English system of university system of education and how to do a project and so on. David was head of the department at that time, so he didn't have much time. He gave me a hard problem, I considered it very hard, of course, and I tried to solve it. So I asked, so there was a mathematical question as well involved. I remember I went to the Department of Mathematics and I asked the professor about it, and he said he couldn't help me. And surprisingly, he went afterwards to David and said, "Oh, I found the solution. That's the solution." He tried to scoop me about it, which it really infuriated me. But David said, it wasn't the correct solution because of this and that theorem. So the problem is still open. So
okay,
really motivated me. Made me really move me into solving the problem. I locked myself in the library. Sussex University, and opened several books, and eventually I managed to solve it, which was a great feeling, and that was quite nice experience.
What was I'm just curious. What was the problem? Do you remember?
It had to do with Dirac fermions, which are a relativistic version of fermionic particles defined on a sphere. So David was interested about it, related to convectified dimensions and how particles could live in these dimensions. Surprisingly, at the same time, so you basically had to solve a differential equation, which was hard for me. I hadn't done anything like that before. Surprisingly, eventually I solved it, and my cousin advised, recommended that I write a paper about it. But, after I finished the project, I just wanted to have holidays, go back to Rhodes, and
right.
I wasn't thinking about writing papers. And subsequently, when several couple of decades later, I found out at the same time another group of scientists in Spain wrote a paper about these solutions related to graphene and the fullerene. Which again, graphene describes relativistic fermions, and then the fullerene, which is the buckyball, the spherical configuration of graphene, it has the relativistic fermions on a sphere, which is the same problem for a different purpose, of course. So, so it was very interesting.
Wow, that's really interesting how that project of yours then kind of came back full circle and later on in your career when you got interested in graphene, right? And
that's right. Yes, wow. Indeed.
How
interesting.
Yeah. So you then did your PhD at the University of Durham, right, in high energy physics. And subsequently, you've been at various institutions, including MIT, University of Cambridge, Imperial College London, and presently the University of Leeds. And meanwhile, your research interests have shifted, right? Can you comment on how and why your research interests have changed over the years?
That's right. Yeah. So I also went to Slovenia for 3 months and to Moscow for another 3 months.
So, there was a long list of institutions.
That's right. So why I want
that's
right. Absolutely.
Yeah. What I'm most familiar with. Yeah.
Why I just wanted to list all of them is because of really my career and topics and places I went. They have to do with lack of necessity. Of course, you have some initial idea what you would like to study. I wanted to do string theory and theoretical physics, and my supervisor in Durham switched me more into quantum field theory and open problems like confinement or quark confinement. But this problem, I carried it with me when I went to MIT. I really wanted to go to US. That was something that, I wanted to experience the education system there, or research system there as well. And I worked a little bit on string theory there. Again, I went back to it, and then I switched back to confinement and such, and a little bit of gravity back there, although I didn't publish anything. Then after that, I realized that theoretical physics and confinement and string theory are extremely crystallized problems. They're old problems. Most of the easy questions have been answered, and what remains are very hard problems. And it's not good for your career when you're young to work on such hard problems, old-fashioned problems, because you can't produce results, and nobody knows you then if you can't write papers. It doesn't matter how much you work. So I switched out of lack of necessity, and I became interested into quantum information. So I got exposed in it at MIT from some initial talks, and I liked it. So I started working on it. I found a job subsequently on quantum computation, quantum information in Italy at ISI. And that blew my mind. I thought it would be hard to change the topic, and it was, let's say, emotionally hard, but I used exactly the same methods and approaches as I had in the high energy, and that was my strength, let's say. And at the end, I managed to come back to interests I had in the past at the very beginning. Though now I'm equipped with a variety of different approaches, and I'm happy to use new things to combine new topics together, or different topics together, and create new ones, which is, I believe, a strong part of physics that helps you a lot.
No, definitely, yeah, that's very interesting. So, as I mentioned in the intro, you're the author of an introduction to topological quantum computation, and that's been a primary research interest of yours now for many years. Some of our viewers will have heard about quantum computing and the race that's on at the moment between companies like Google to build the first useful quantum computer. However, not many will have heard about topological quantum computation. So briefly and in simple terms, remembering that our audience is mainly going to be sort of A-level students and, at that kind of level. What is topological quantum computation about, and why is it so fascinating?
That's right. Yes. So topology is more of a branch of mathematics that is combined or comes from geometry. So geometry describes shapes, and it describes actually the exact form of shapes, the curvature, and so on. Topology is a particular characteristic of geometry that doesn't care about the exact form of shapes, but it cares about characteristics that do not change by continuous deformations. For example, if you have two links, two strands, if you cross one with the other, that creates a link between them. And that linking is a topological characteristic. So two strands, two rings which are not linked, they have trivial topology, and two that are linked have a non-trivial topology. Okay, the shape of the links, the exact geometry of the links, it doesn't matter. So the topological characteristics is regardless of the shape of the links, are they linked of this rings, are they linked or not? So that's the distinction between geometry and topology. And topology is a very stable, because if you change the geometry, the topology stays the same. The linking, let's say, of the strands or of the rings stays the same. And stability is something that, it's very important in quantum computation, because you deal with very small particles. They're easily disturbed and changed. It's very hard to isolate them completely from the environment. So stability is a paramount importance. That's the only thing that slows down our progress on quantum computers, building them and using them. Surprisingly, there are many quantum characteristics of matter, of quantum physics, that have topology in them. So the topological characteristics in quantum physics, they're not easy to find. They're very, you need to think a lot and work hard about them. But then after you understand them and after you recognize them, then you can see them all around. So there are many materials, let's say about 15% of the materials that you could possibly construct, they are of topological nature. They have topological characteristics. So they are quite widespread, really. And that's really, then the idea is to use these topological characteristics in quantum computation to give some stability, some a happy island where the waves won't kind of smash everything, will keep things calm, and you can focus there and do your quantum computation. That's why topological quantum computation was created. And up to now, yes, it's been hard to it's been hard to detect it or to use it. It's been employed indirectly in many different areas in quantum computation.
Yeah. So just to pick up of what you just mentioned there, the field, has suffered. So the field of topological quantum computation, it's suffered some setbacks on the experimental side of things in recent years, with experimental claims, some of them failing the test of reproducibility, and some concerns over cherry picking of data. Given this, how do you view the prospects of the field?
That's right. So indeed, there is a lot of controversy in the developments. There's a lot of work in leading universities and experiments to discover these, let's say, anions. These are type of particles that they're effective. They're not elementary, but they emerge in materials, but they have particle-like behavior. And these particles, the anions, are you can use them for topological quantum computation. Now, the discovering the existence of anions is something that in the laboratory is something that will get a Nobel Prize. So, right. The stakes are so high that, of course, there is a lot of controversy. Of course, when somebody tries to do that, many others try to do it at the same time. And if they announce a result, people will immediately attack them and say, no, it's not right. It could have been many other things. Now, of course, this is healthy. This makes people work harder and find more irrefutable arguments why results, experimental results that for the existence of anions. But at the same time, it shows that it won't be settled easily. As I said, if the lab or the scientists who discovered the anions conclusively, they will get a Nobel Prize. So it's a very big result.
Right.
So I don't quite see that they're not as a setback to topological quantum computation. I see more of okay. If you had anions, you could do many things, but already that's a big a big goal to achieve, and hopefully it will happen. I'm pretty certain it will. It's just a matter of time.
So you probably the theoretical underpinnings are so strong. You suspect that will just be a matter of time.
That's right. It's definitely a function of money and time.
Right. But yeah, even if I think it's worth pointing out that even if I think you alluded to this, even if the topological approach to quantum computing doesn't pay off, it's already provided so many fruitful and interesting ideas that percolated through to more conventional quantum computing anyway. So it's been a very useful field of research, right?
Yeah, that's right. The error correcting codes we have in quantum computers that they use in experiments are actually taken from topological quantum computation because they have very nice geometrical configurations, which are then simple for the experiments to adapt. So there are already applications, direct applications.
Right.
Yes.
Right. So a recent paper of yours explores how the quantum nature of gravity may be probed via experiments involving cold atoms, which may lead to a better understanding of black holes, amongst other things. Viewers may be surprised to hear that laboratory experiments may offer a route to such understanding. In simple terms, how is this possible?
That's right. So yeah, I'm thrilled to work on topics like the relativity and so on that inspire me into physics to begin with. The method now, this simulation, what it is you can think of it as another way of understanding nature. For example, in engineering, if somebody wants to build a bridge, they can calculate it's how strong they have to build it and what materials to use and so on. But at the end, they might build a small prototype where it uses the same kind of characteristics, and then you put in turbines in air channels and so on in order to see its stability, or hit it with waves and so on in order to see how it reacts. And to a very good extent, these prototypes they build, they give lots of information about how the big bridge would behave. So this is a very common method that they use before they invest a lot of money to build a certain structure. So the same thing, you can use now the same thing for understanding objects in physics that you don't have direct access to, like black holes or quantum gravity. This quantum gravity involves energy scales that are way beyond anything we can do in the laboratories and the biggest colliders. Or black holes, we can detect them through the gravitational waves, but this is a very weak signal still. It gives us some characteristics, but nothing related to the quantum aspects of black holes. So what a suggestion that quantum information gives is to do the quantum simulation, to build a system that behaves similar to a black hole. It has the geometrical characteristics encoded and has the quantum physics encoded there. And then you build it, and then you start studying how it behaves. You want to see certain characteristics like the Hawking radiation, for example, that Hawking predicted. So, but this is just a prediction without a big theoretical background. So being able to simulate it and see actually that the prediction of Hawking is there, it will be a fantastic achievement. So yeah, that's this new area, let's say, I got the last few years, and I'm very excited about it.
Yeah, no, it's absolutely fascinating. So if we kind of switch topic to the teaching side of things, you've taught undergraduate physics students for a number of years. What do you perceive to be common problems that students have in making the transition from A level or equivalent to degree level? And yeah, how do you think students can prepare better for the transition?
Right. So, I mean, from personal experiences, also seeing students, I would, my best advice is really, I understand that it's a hard time to move, from the A levels to the university. It involves many changes, the place you live, the way, how the occupations, your friends change, your circles, and the way you study changes, and the amount, the topics you study, the amount of material you have to study changes. So there are many, many changes there. So my advice is good to be open to change, how to change things, keep things that you believe that work for you, but at the same time be open to change, to adopt new techniques, to search, to find ways that are suitable to this new environment for you, new habits to study at the library or study at home or at the university. Make sure you have a big circle of friends and fellow students you communicate, because information is important. I think that helps a lot. And also understanding common problems and difficulties helps a lot. And, as at the same time, I would advise, have a book with you, read books, just get books and make them your friends, and they will become friends of yours, and they will support you during your studies. So I think that's a good thing to have in mind.
No, that's very good advice. For sure. I'm just curious, have you perceived issues in terms of students having problems in terms of switching their mode of thinking, if you like, from A-level physics to degree-level physics? Because obviously, so the way you think about physics, there's a fundamental change, right? Have you perceived some students struggling with that?
That's right. I mean, this is changing the way you think or learning new things is what life is all about, right? Sure. I mean, in physics, of course, you learn always new things. And as long as if you like something very much, then any difficulties you face, you're going to overcome them. And that's a good characteristic. Make sure you like what you're doing. And of course, there are difficulties. Then how do you overcome them? That's the important question. It's, if you're excited about what you're doing, about the new things you're learning, then that's fine. You must stay behind in some topics. It's all right. Then you can go back and revise. That's all right. So if you see there's something normal, and being willing to learn continuously, then I'm sure you do well at the university. There's no question about it.
Outside of physics, you have interests such as karate and dance and theatre. Do you see any similarities between those activities and doing physics?
Right. Yes. I mean, karate, I did it from a young age. It gives you confidence. That's the most important. Determination, and so on, and patience. So yeah, that definitely helped me throughout my life. About the dance, actually, it's how I got involved in that is I wanted to, people say that our brain is there in order to help us move in space. So it's one of the most complex aspects that the living organism needs to do. So they create a brain to do that. And an expression of it is dance, of course. And I wanted to bring a professional dancer, street dancer, actually, to perform at the university, at the physics, at the undergrad students. And then I will explain them about the complexity of the movements and how how the brain automatically solves, complex problems but eventually what happened is that I got involved in his performance, and we actually performed together a physics dance kind of experimental performance on stage twice at the university. So I was very thrilled to collaborate with this artist, the dancer, as well as a director who directed the whole thing. So it's been a fantastic experience. You can find it on YouTube and maybe laugh about it.
If you're happy for me to share the link,
sure. Yes, of course. And
I'll leave
it for
people to check out. Yeah.
Yeah, I think there are many other activities that, as I said, that they involve the brain, and they are very important to life apart from physics. But somehow physics got hijacked the terminology of clever and smart. If you want a representative of something smart, you put Einstein there, and everybody thinks, yes, that's right. Yeah. But I think poetry is equally challenging and intellectually. And why not having Oscar Wilde, for example, if something was smart, and have Einstein? I find that biased, even if it's for physics. I still don't think it's racist. But it's all equally important, I would say.
No, that's a really good point. Yeah. And in fact, that the dance performance you mentioned, I actually caught one of those back when I was at Leeds. I think it was in 2012. So yeah,
that's right.
Breaking Point, right? Which it was good. I'll leave a link for that if people want to check it out. And finally, Jiannis, what's the most inspiring thing about doing research in theoretical physics?
Right. So the characteristic I like is that it gives you kind of a rigid, a solid, with facts, something that works no matter what. It's not relative, right? And this, it gives you kind of comfort finding things how they work. Many things in life are very relative and change with time and so on, which might be a bit unsettling, but it's how it is. But I have to admit, what I enjoy most in physics is communicating with other people and discussing, going to conferences and so on. This fantastic, actually, experience to share ideas. Ideas are extremely precious, and meeting other people and offering freely, what they worked on very hard and came to some new ways of seeing physics or nature. And sharing it with you and freely. I think that's just amazing, and I think it's very precious for me, and I enjoy it very much.
Certainly I can I can understand that, even from my time in physics, just the whole just being part of a community of like-minded people and sort of sharing that sort of feeling of bonding with them. That's great. So thanks, Jiannis, for joining me, sharing your thoughts and your research.
Thank you very much for your time. Yes, thank you.
And I will leave links for Jiannis's book and Jiannis's YouTube channel, where you can find his lecture on Decoding Quantum Mysteries, which was sort of a celebration of you becoming a professor, if I'm correct. And also the dance physics performance Breaking Point that he performed in. So thanks for listening, everybody. Don't forget to like and subscribe if you haven't already. Leave a comment as always. It'd be great to hear from you. Take care, and I hope to see you soon. Bye.
Bye-bye.